So let's have a look at problem 19.1, and this is again example 11.1, which we saw in problem 11.1, where we just used the h2 syn command to design an h2 optimal controller. So we will now do this via linear matrix inequalities. Well, if you're not sure how the LQG problem can be represented as an H2 design problem, I recommend that you have a look on problem 11.1 first. So here we will now talk about writing the H2 optimal control problem as a linear matrix inequalities, which could then be solved using convex optimization tools. So let's write down the setup of the problem first. We have a generalized plant of this form, where W to Z is the performance channel. The controller measures the signals Y and has a control input to the plant U, and the controller is parameterized by state space matrices AC, BC, CC and DC. So the problem is now to find these matrices AC, BC, CC and DC that minimize the closed loop H2 norm of the transfer function from W to Z. So that's the H2 problem. And now we are talking about output feedback, because we only assume that the controller measures Y instead of the full state vector X. So we've seen that leads to a dynamic controller, and that's why we have the state space matrices for the controller. Note that the state feedback case, which we will consider in the next problem 19.2, would have an optimal static controller with so basically AC, BC, CC are all 0, and the controller is parameterized only through DC. We will see this in exercise problem 19.2. So for now we will stick to the output feedback case, and let me point out here that if we understand the output feedback case for this problem, we can easily use the same ideas to derive linear matrix inequalities for output feedback problems for minimizing the H infinity norm, for example. So I will now like to go into the details of finding the LMIs that we can then code using CVX to find an output feedback optimal controller for minimizing the H2 norm. So in order to discuss the general ideas for output feedback controller synthesis, let's write down first the block diagram in a somewhat different form. We have the plant here, where the W to Z is the performance channel, output Y and input U is coming is the control channel. So the controller measures Y and exerts U on the plant, and the controller is parameterized by matrices AC, BC, CC and DC. Now I will represent this in the form of a block diagram as shown here. So now these blocks are just static matrices because we can represent this with an integrator. So this is x dot, this is x, so we would have x dot is equal to a1x plus b1w plus pu, that would be x. Similarly, the controller states could be represented here. Xe dot is acx plus bcy and u is ccx plus dcy. Now this can be combined in a sort of similar fashion to write down the closed loop transfer matrix using an integrator where now we can define this theta dot as x dot and xc dot, and theta here is x and xc. So what we've done is stacked up the controller and the plant states together in a vector theta and use the same idea to write down the closed loop. Now we can write the closed loop matrices A, B, C and D using the matrices A1, B1, B, C1, D1, E, CF and AC, BC, CC, DC. So let's try to also do that quickly. So we will have A, B, C and D given Y. So now let's have a look. The input to the AC this block, so this calligraphic A, B, C, D block is X, XC and W, and the output is X dot, XC dot and Z. Now we want to write this this block diagram, use this block diagram to write the closed loop matrices. So let's start with this block here, the control block. The control block receives XC and YC as input and outputs XC dot and U. So let's try to write that down as it is. Now I will write down AC, BC, CC and DC as it is. The inputs are to the control block AC, BC, CC, DC are XC and YC, and YC is C times X plus F times W. So the input here, input to this block is X, XC and W. So in order to get the XC here, we have 0, I, 0. So if we pass X, XC and W here, we will get XC in the first channel and we want Y in the second channel, which is CX plus FW. So that's what we get on the right of the control block. To the left of the control block, we need to get X dot, XC dot and Z. So X dot, the X dot equation has B times U. So the second channel is U, so we have B times U. The second row is XC dot, so which is the first row here, so we just swap the first and the second row, and the third one is Z, and the Z equation has E times U here. So we have 0 E here. Now the second row of this matrix is already x dot, so that would just be zeros. And now we have the first row, which is x dot, is ax plus p1w plus bu we've already considered, because this row, so 0b times u, which is coming here, is captured, so we don't need that. And the z block is then just c1x plus eu, that we've again considered here, so we don't need that, and f times w, d1 times w. So you can just verify that this is correct by looking at this block diagram. So this is what we get as the closed loop ABCD matrices. And now, as one more step, we can just write this down explicitly. Now you can just do this calculation. To verify what I'm writing down is correct. So that's our closed loop matrices ABCD. Now let's look at the analysis condition first. What does that mean? That means, given a controller in the form of a state space model AC, BC, CC, DC, is the closed loop system, which is what we just derived here, is the H2 norm of the closed loop system less than gamma. And this is called the analysis condition. So is this true? And the LMIs that answers this condition, we have seen this in an earlier exercise and also in the lecture notes, is here. So if there exists a positive definite P such that P plus PA, PB, P transpose P minus gamma I is negative definite, P C transpose CZ is positive definite, and trace of Z is less than gamma. If this is true, then we have that. So let me just shift this to the left slightly. If this is true, then we have that the H2 norm of the closed loop system is less than gamma. Now this would be the analysis condition, but for the synthesis condition, we don't know the closed loop matrices A, B and C, and that's because we don't know the controller. So what we want now is to find a controller in the form of AC, BC, CC and DC that sort of gives out a closed loop A, B, C that satisfy these conditions, and that's what we want to do now. So now the synthesis question is to find AC, BC, CC, DC such that the closed loop system has an H2 norm less than gamma. Please note that when I write the system in this form, I mean the dynamic system, not just the matrix A, B, C, D as we have here. So this is just a static matrix, but this along with this integrator is a dynamic system, and when I write H2 norm of this system, I mean the H2 norm of the underlying system with the integrator, not just this matrix, because H2 norm is defined for dynamic systems and not for matrices. So please keep a note of that. Now the key problem is that if we just substitute for A, B and C the values that we computed here, we have products between, so you see here that we have products between A and P. We have to find a P and AC, BC, CC and DC such that this condition is satisfied, and because we have products, it's no longer a linear matrix inequality. So it's a non-linear matrix inequality because we have products between AC, BC, CC, DC and P, and P is the matrix that we want to find along with AC, BC, CC and DC. So now there is a trick that we will see to make a transformation so that we do obtain linear matrix inequalities, and that trick is in the form of a congruence transformation. So what we want to do is to find a clever matrix Y such that if we do a congruence transformation on our usual matrix inequalities, which I will quickly write down again, or let me just write down the matrices involved in these matrix inequalities. If we do a congruence transformation with Y and with Y00 identity, and also a congruence transformation here. So by the way, the C transpose is here. We get these matrices, and now the trick, so we do the same congruence transformation here. the trick now is to select a clever y such that these conditions are linear matrix inequalities in some new variables. And now let's see how we want to do that. Let's first look at the terms appearing here. So we have one term which is y transpose py, one term which is y transpose pc, sorry, this should be y. We have one term which is cy, we have one term which is y transpose pb, and here we have one term which is y transpose PAY. Note that the other term is just the transpose of this, and this term is the transpose of this term. So we have three terms here, 1, 2 and 3. If we make sure that these three terms are linear in some new variables, then we have a linear matrix inequality here after the congruence transformation, and this is exactly what we will do now. So let me write down the new and the old variables. So we now write down first the old variables. Let me write those down in red. So we had to look for a P and AC, BC, CC, DC, and of course a Z and a gamma. And now we move from these variables to, let me write down the new variables. So we will see what these variables are: x, y, k, l, m, n, and the z and the gamma stay as it is. So these are the old variables that stay as it is. So we need a transformation from these variables to these variables. So let me call these variables v, just for the ease of notation. Now the clever choice of y, so let's write down the p, which was, so let's call these old variables, and these new variables. Now if we write down the p, which is an old variable, as x times u transpose and some star that we don't care about, and also the, so, and if P inverse if we write as y, sorry, the new variables we write for blue, y, and some auxiliary variable v transpose and something we don't care about. So if this is P and if this is P inverse, the clever choice of y that does the job turns out to be y I v transpose and 0. So if we choose this y, then it transforms these non-linear matrix inequalities to linear matrix inequalities, and we will see how. So this guy does the job. Let's look at each inequalities now. So we had the first one was just P, have Y transpose P Y. You can verify this, but this is nothing but Y transposed V I 0 times P is nothing but X U transposed star times Y. So that is Y V transposed I and 0, and you can verify that this is nothing but Yx I. So that would be the first transformation. Now for the other transformations, we see that we have these three terms, right? We have these three terms: Y transpose PAY, then we have Y transpose PB. So this term, let me remove that one here. So this is the first term, this is the second term, and this is the third term. Now if I collect all these terms in a matrix and write down Y transpose P A Y, we have Y transpose PB, then we have CY, and we don't need it for H2 problem, but if I still write down the closed loop matrix T, which is untransformed, I define this matrix by collecting these terms, and this T, we just collect it even if we don't need it, because this procedure is more general and can be used for other norms. So for now you can disregard the D. What is important is the 1 block, the 1 2 block, and the 2 1 block. Now with this choice of Y, which is here YI V transpose 0, and with the block structure of P, which is here XU transpose, something we don't care about, and with A, B, and C and D that we found above, which is these guys A, B, C, and D, these are the closed loop matrices, we see that this thing can be shown to be equal to be this. Now I encourage you to try once that this is indeed true. So all you have to do is substitute for this calligraphic Y this clever choice, then substitute for P this block, and of course because we have PP inverse equal to identity, we have in the first block we have XY plus UV transposed, and then something. So this thing has to be identity, and we will use this fact later. Now if you substitute for P, Y, A, B, C, D, the values that we have computed above, see that this is equal to this. Expression, this long expression here. Now you see that in this expression, this is all linear terms in X and Y, and these are the terms where you have products. So for example, you have the old variables represented in red, AC, BC, CC, DC is having products with the new variables x and y, and here you have a product between x and y, two new variables. So what we do now is to call this whole term K, L, M and N, and these are also the new variables. So if we then write down everything again, get AY, A, B1, 0, XA, X, B1, C1, D1, C1, Y plus 0B, I0, 0E times KLMN times I00, 0CF, and here you have KLMN. So you can see that now this thing clearly has no products. I mean no products between variables. So KLMN, X, Y are appearing linearly, and if we just write this down as a final thing, we get this thing here. And now you see that this is completely linear in x, y, k, l, m, n, which are the new variables. Recall that this we derived this from this here. So let me just copy this here. I don't know why it jumped there. So this is equal to this, and now let's, for the sake of notation, call this thing a of v, because this is a function only of new variables. Let's call this, so the v, let me just use this one for v, that's still the new variable. Let me call this p of v. This is c of v, and this, even if you don't need it for h2, you might need it for h infinity. So this is d of v. So we've found a clever y such that these terms are transformed to linear in these new variables. So to summarize everything, what do we have? We have that these inequalities, let me write down the old ones first. So A transpose, this was the closed loop A, and remember that this was a function of AC, BC, CC and DC. A transpose P plus P transpose A, which was again a function of AC, BC, CC and DC. Let me just reduce this and just write down P, PB, P transpose P minus gamma I, 0. So So these are the old LMIs, old non-LMIs and non-linear matrix inequalities, and the non-linearity because of these products, and A contains these functions. You have these products. So we found a clever Y such that if we transform these nonlinear conditions via congruence transformation to linear conditions, these could then be written as, so we have these y transpose py. We saw that y transpose py is this. Let's call this thing x of v. So we have this thing is nothing but x of v positive definite, and that is linear in x and y. Then we have the y transpose pay plus the transpose of that. We saw that y transpose pay is a of v. So we have a of v plus the transpose of that. Then we have y transpose pb, which is here, which is p of v, and the transpose of that here. That one stays as it is, and we have y transpose py again, so that is just x of v, and we have cy here, which is just c of v, and z stays as it is. So this is nothing but x of v positive, then so a of v plus a of v transposed, then we have p of v transposed minus comma I negative definite, and again x of v here. We have c of v and c of v transposed here, and z, and the last condition is just as it is. So here we have linear matrix inequalities in v and z and gamma. So let me write these again, because these are still the old variables, we did not transform them. And v are x, y, k, l, m, n. And if these matrices exist such that these LMIs are true, then we have that the closed loop system has an H2 norm less than this gamma. But what is still left is only knowing that the closed loop system can have a norm less than gamma is not enough. We need to find the controller back, and that's why we have to reconstruct the controller or the controller matrices. So in other words, go back from x, y, k, l, m, n to a, c, b, c, 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 d, c. So let's see how we can do that. So just recall that we made a substitution here. So let me just copy that thing down. So we made this substitution KLMN was set to be equal to this, so we will have then KLMN minus XAY. Oh, there's supposed to be a plus that I'm missing here, so this should be a plus. I'm very sorry, should be a plus here. So let me just change this. So plus here, and we set this to KLMN. And similarly we have a plus missing here, so then I can move the XAY to the other side to have this times we transpose 0 C I inverse. So you move this to this side and then pre and post multiply by the inverses here. So let me move this further to the right to have again U. So this C should be black. Have U, then we have X P 0 I inverse. This should be equal to the matrices that we want, AC, BC, CC and DC. So once we solve these LMIs, we do have X, Y, K, L, M and N. So we do have these guys, but we don't have the U and the V, and this is where the other condition that we saw, this one, comes into play. We know that XY plus UV transpose is identity. So what we know is that XY plus UV transposed is identity, so we can do an SVD of I minus XY and factorize this matrix to get U and V transposed. So once you have that, we can plug it in here and get the controller matrices back. So now let's have a look at some section of the code. you see here the XV, AV, PV, CV and DV as we've defined it above. So here, so this is what we called AV, PV, CV, DV, and we called this matrix XI, IX, XV, and this is exactly what is being defined here. So XV, for example, is just YI, IX, EV is A Y plus PM, A plus PNC, K, and XA plus LC. So this is just a part of the code, so I'm just showing you this code so that you understand better when you look at the MATLAB code yourself. So this gets as an input G, which is a structure containing these matrices, for example G dot A, G dot B, G dot B1 and so on, and that's why you see these things here. Okay, so once these XV, AV, BV, CV and DV matrices have been defined, we can now write down the LMIs. So this section of the code now shows the LMIs that we just derived. Here we have AV plus AV transposed, PV, PV transposed minus gamma I, XV, CV, CV transposed and Z, and Z minus gamma H2, a trace of Z minus gamma H2. So we basically want LMI 1 to be negative definite, LMI 2 to be positive definite, LMI 3 to be 0, and LMI 4 to be negative definite, because that's what you really want is trace of Z less than gamma, and that is the same as saying trace of Z minus gamma is negative. And now let's see how the optimization problem looks like. So that's the section of the code where we write down the optimization problem, and as we just discussed, we minimize our gamma subject to LMI 1 negative definite, subject to some tolerance here, LMI 2 positive definite, LMI 3 0, and LMI 4 negative definite. In this case, because it's just a real number, LMI 4 to be negative. Now one quick note about LMI 3, which we did not discuss yet. So LMI 3 is saying dV to be 0, and that's because we want the closed loop transfer function to be strictly proper, because otherwise the H2 norm is not even defined, and this is basically incorporated in LMI 3. So now let's look at controller reconstruction and some numerical aspects. So what we do when we reconstruct the controller parameters AC, BC, CC, DC is we do an SVD of I minus XY. Now note that our X of V was YI IX, and we had this as one condition. So this would imply that I minus XY should not have any eigenvalues or singular values at 0. But what might happen and what does happen in practice is that there are some eigenvalues or singular values that are very close to 0, and uh, if this matrix is ill conditioned, if we factor this out into U and V transposed, which we then use to reconstruct the controller parameters, the controller parameters are not reliable anymore. So in order to avoid this, we will follow a numerical procedure. But before we do that, let's look at the code that does the controller reconstruction once we have made sure that this matrix is well conditioned. So here you see the snippet of the code where we do exactly this. This is the SVD step. Then we compute UV transposed, and then we compute the two inverse steps. Let me just go back here. Yes, here. So we first compute this difference, then we compute this one by solving a set of linear equations, and then we compute this whole thing to get the AC, BC, CC and DC matrices, and this is done in these three steps here. So the K here is basically just this matrix composed of controller parameters. Now let's quickly look at the numerical aspects that we just discussed. So how do we make sure that this matrix is not ill conditioned, so that the controller parameters that we obtain via this procedure are reliable? So what we do is we follow a three-step procedure, and this is recommended in the lecture notes by Scherer and Weiland, and this is already implemented in the code, so you should have a look at the code to locate this three-step procedure and understand exactly what's happening. So in the first step, we simply solve the usual problem, so which is minimize gamma subject to x of v positive definite, this matrix negative definite, and this matrix positive definite along with trace of z less than gamma. So that's our standard problem that we discussed. Now what we get out of this is gamma star. Now we relax this gamma star by some relaxation factor, say 5%, and then solve a feasibility problem in step 2. So let me just write down these LMIs again. So I will just copy them. So now for the second step, we use this relaxed gamma opt here and add some regularization to our original constraints, and we minimize this regularization factor alpha. So let's see what this problem does. In problem 1 we get the usual gamma star by the usual LMIs. We relax this gamma star and now impose that gamma opt as constraint and not minimize it here, but instead we minimize alpha, which is a regularization parameter, which is punishing a large x, y and klmn parameters. So we try to get x, y, klmn that satisfy these conditions. So these conditions simply mean that the closed loop system has an H2 norm less than gamma opt. Remember that gamma opt is no more optimal but a suboptimal condition obtained by relaxing the optimal gamma that we obtained in step 1. So we now choose x, y, k, l, m, n that satisfy this condition, and the variables that have the minimum norm in this sense. And now these are not LMIs, but we can convert these into LMIs as here. So x, because we know that x has to be positive, definite and symmetric, we can just impose this here, and for the KLMN we can impose this condition. You should have a look at why these are equivalent. Note that KLMN is not square, so we could not just do this like we can do for x and y, but we have to use this. A simple sure complement argument will make it clear why these are equivalent. So now here we regularize x, y, KLMN, or in other words we obtain x, y, KLMN that make the closed loop system have an H2 norm less than gamma opt, and the values of x, y, KLMN are as small as possible in some sense. So now here we obtain alpha star. We again relax it by some factor, say 5% for example, and then we solve a third step. And in this step now we want to make sure that the matrix I minus xy is not ill conditioned, or in other words we want to push the y away from x inverse, and this can be achieved by imposing a condition like this. Observe that this condition along with the sure complement argument makes sure that y is at least beta away from x inverse in some sense. So you should make sure you understand this step. Why is this equivalent to pushing y away from x inverse? So once we understand this, then we solve a third optimization problem. So let me first bring all the conditions here, because these are as it is. So now here we use this relaxed alpha opt. So also alpha opt here. So I will just replace these modify these. So let me just write this one again. So these are what we had before in step 2, and now we add another constraint which we just saw, which is x beta I y positive, and then we maximize with respect to beta. So that forms our final step. Note that for beta equal to 1 we already have feasibility of all the other conditions, so this problem definitely is feasible, and there exists at least beta equal to 1 which gives feasibility of all the other conditions. So now we try to maximize beta, and maximizing beta simply means pushing y away from x inverse. And then once we obtain x, y, k, l, m, n here, we reconstruct our controller parameters as we saw above. So so you can either choose to do this or not. So you can either be happy with the solution that you get here as long as the matrix I minus xy is not ill-conditioned, or you can try to regularize this and then improve the conditioning in these two steps. So once we do that, let's have a look at the results of the controller that we obtain via the CVX code, via the LMI lab code, and the h2syn command that we've already seen in previous exercises. So I should say a few words about LMI lab. So LMI lab is another linear matrix inequality parser, which also runs the SEDUMI or SDPT3 solvers, as does CVX for solving the convex optimization problem. H2syn, on the other hand, you've seen before, is also a MATLAB inbuilt MATLAB function which can be used to compute the H2 optimal control. And you see in this figure that we get identical controllers using all three different methods, which is what we will expect. And now, just for the case of showing what the closed loop system with under feedback looks like, and these are the closed loop sigma plots, and now you can see that the closed loop system is strictly proper, and yes, so we get identical closed loop systems, and that's because we get identical controllers via these three different methods. So these are essentially not three different methods but three different tools, and you would expect these to be the same. You can now try to use, so this is without the relaxation steps. You can try to now use these relaxation steps and see how the controller that you obtain is different, slightly different than what you get without the relaxation step. So that's it for this problem. Thanks a lot.